Hi, everybody. Today's lesson is for Monday, April 13th, 2020. Short lesson today. Really, I'm just going to go through sort of some admin stuff and then quickly show you guys a screenshot of how I set up my wave calculation spreadsheet for project one. But really, please use this time to work on the project, make use of office hours. Please jump in and, ask me any questions you have. Happy to compare numbers, formulas, etc. So let's go ahead and jump to the notes. All right, great. So again, this is all I have for you guys today. Just a couple kind of reminders. Homework 8 is posted. It's officially quote unquote due April 15th, but again, all those problems are optional. Really, I just want you guys to have that as a tool to study for exam 3, the final exam, kind of, pending some more information from the leadership on how that process will go. And also the big kicker is project 1 is due on Friday. If you guys think you might need kind of a little bit more time to work on that, send me a note. I'm happy to push that deadline to Monday because I'd rather you guys spend more time on the project than try, really make sure you really understand it than try to just submit it very quickly by Friday. I do plan to assign project 2 on Friday. Project 2 is a little bit different. It should just be a little bit more of an opportunity to look at sort of a real world ocean structure, talk about maybe how it's similar and different from the structures that we've studied in classes. We've done a lot of simplification. So just kind of a chance to sort of think about how we have some other, I guess, uncertainties when we're looking at these more complex structures. Brief review of last time, lesson 33, we talked about 3 different methods to find when the wave force will be maximized. As a reminder, those 3 methods are either by definition, so you can take the derivative of your force equation, set it equal to 0. That time will give you the time of the maximum or minimum force. You can also do something like plot it in Excel or MATLAB and sort of see when it reaches a peak and what the corresponding time is. And then finally, we stepped through in Excel how to set up Solver and use Solver as, the very powerful tool that it is to calculate when that wave force is maximized. And that's what I did when I calculated the maximum wave force when I solved the project recently. Also, we talked about how to use Simpson's rule to find the total wave force on a pile. So again, we're splitting it into n different segments for this class. That gives us 5 points where we'll calculate the force per unit length. And we can use that equation to calculate or estimate the total wave force acting on that pile, as well as the resultant force. And the way we've calculated it, that would be the force distance below the still water level. The really plan for today is just make progress on project 1. So like I said, please jump into office hours at any moment. Shoot me a note if you're working on it outside of online office hours, and I'm really happy to try to get back to you as quickly as I can. But before I jump off, I will share my screen and just show you the example spreadsheet that I set up in Google Classrooms. I showed this briefly during lesson 33, but this is now posted. This is in the Google Classrooms, but it's also uploaded in the project folder in Blackboard. I like to have things that don't change sort of on top. So I have all of the wave properties. These I just input. These come from the problem statement, our wave height, the water depth, the wave length. From there, you can calculate your wave number, your frequency, and then your period. We also know our pile characteristics. Since we just have one pile, you can input x equals 0. I have an arbitrary time set up right now. This is what will change when we're maximizing our total force. Drag coefficient, inertial coefficient, the pile diameter in units of feet. Our thickness in units of inches, that doesn't really show up in these calculations, but it could be helpful if you want to continue to use a spreadsheet for API calculations. Exposed length, I think I need to change that. I was playing around with something earlier. And then I have a bunch of different depths. So the highlighted depths are the 5 depths that I used when I used Simpson's rule by hand when I did that hand sample calculation. So again, we're splitting it into 4 even segments. 20 feet is our delta Z. And we're going to calculate the total force. I broke this into a lot of sub-calculations just because it's easier for me in Excel than having one enormous equation in one cell that's sort of a little bit harder to track. So first I calculate our coefficient, K sub X. This is that cosh, K times Z plus D divided by sinh, KD. Our current is going to be 0. Our wave x velocity, we can calculate using that equation from your waves equation sheet. And we also talked about it in class. U total is the sum of those, and then absolute value. It's important to have both of these, not just squared, because that'll preserve the sign or the direction of your drag force per unit length. Also have that equation for the x acceleration, which is again k sub x times h pi divided by t squared. That equation, look at the equation sheet, don't listen to me right now. But that'll go into the calculation of our inertial force per unit length, F sub I. And then finally, our total force per unit length is the sum of our drag force plus our inertial forces. Next to that, I have a column with the Simpson multipliers. And so we can calculate this at any moment. Our Simpson multipliers, again, if I were doing this by hand, I would just pull out F sub x at z plus d equals 80 feet, z equals negative 20 feet, z equals negative 40 feet, z equals negative 60 feet, and z equals negative 80 feet, z equals d equals 0. And I would use the Simpson equation, so delta z divided by 3 plus the force times my Simpson multiplier plus the second force times my Simpson multiplier, et cetera, et cetera, et cetera. I have all of these other forces because the more segments you have, the more accurate, the closer you are to your actual function. So I set this up with 20 actual segments. So for Excel, it's really easy to drag and drop. This F total is just going to be the sum product of our F sub x times our Simpson, the sum product of those, and that quantity times delta z, which for this would be 4 divided by 3. Similarly, for my numerator, I can take the sum product of z times F sub x times Simpson, divide that by my denominator, which is the sum product of F sub x times Simpson, and that should give me the location below the still water level of my moment. I know this is just a quick overview, but I did want to show you guys this, make you aware of this. If you want to check your calcs at time t equals 2 seconds, this would be, a good place to do that. Also happy to compare notes in office hours, outside of office hours, at a time convenient for you. So just, please don't hesitate to reach out. I hope you guys are all doing great. That's all I have for you. So have a wonderful day, and looking forward to talking soon.